Okay, so remember, this is a situation we were in case 3. We're thinking, if we have a complex, if we're trying to solve a differential equation like this, and we have a complex so-called eigenvalue or root of the characteristic polynomial alpha plus beta I, then how do we get a real solution out of that? So we already agree that if alpha plus, let's call it lambda, if lambda equals alpha plus beta I is a root of our characteristic polynomial a lambda squared plus b lambda plus c equals 0, then we already agree that e to the lambda t is a solution to our differential equation, ax prime prime plus bx prime plus cx equals 0. So that is a solution. We want a general solution, and we want it to be real. So e to the lambda t means e to the beta I times t. That's our solution. Our problem is that this is a complex solution. In the last video, we came up with a way of generating real solutions out of complex ones. And it's really simple. Just take the real part, or take the imaginary part. Those are both ways of getting real solutions out of complex ones. So first, we need to figure out what are the real and imaginary parts. It's not so clear, right? Just staring at this, it's not so clear just from the notation what is the real and imaginary part. You have to break this down further. So first, let me write it as e to the alpha t plus beta t times I, just distributing the t. So I've got e to the, and then some real number plus some real number times I. Now, do you remember from an earlier video, in the previous lecture, we saw that e to the a plus bi, or maybe I'll use different letters since those letters are in use, e to the u plus vi is e to the u times e to the vi. And then we discussed what is e to the vi, where v is a real number. We decided it was cosine v plus I times the sine of v. I don't know why. Sometimes I write the I before and sometimes I write it after. So there's nothing wrong with writing sine of v times I. So this is the way of breaking this, something like this, down into its real and imaginary parts. If someone asks you, what's the real part of e to the vi? You answer them cosine v. What's the imaginary part of e to the vi? Sine v. So we break this down using a similar approach. So e to the alpha t times e to the beta t I. And then what is meant by beta t here is it's what goes in the sine and the cosine. So e to the beta t I is cosine beta t plus I times the sine of beta t. And now you can see what are the real and imaginary parts, right? Probably better to distribute this. Like that. And so here is our real part and our imaginary part. So in the previous video, I was calling this thing z, and then here's our x, and here's our y, all functions of t, z of t, x of t, y of t. So what we saw in the previous video is if this is a solution, which we are assuming we're in a situation where it is, then these individual portions here are solutions, and these are real valued solutions, right? No longer complex valued. So let's call them x1 of t and x2 of t instead of calling them x and y, since that's the notation I've been using to refer to multiple solutions to the original differential equation. Let me continue to use that notation. So this, and there's the imaginary part. So these are our solutions. Solutions to the original differential equation, sorry, not this. They are solutions to the original differential equation. and they are real. So we are very happy about this. We are even happier if they are linearly independent. If we have two real linearly independent solutions, then we can write C1 times one of them plus C2 times the other one, and there's our general solution. Then we can suddenly just solve any initial value problem that we want. So are these linearly independent? So question, are these linearly independent? If so, we are going to be even happier. So let's suppose we have a linear combination that equals 0 and see if we can prove from there that the coefficients have to be 0. Okay, so we're assuming we have C1 times this one function plus C2 times the other one equals 0. And now we want to verify that C1 and C2 have to be 0. So plugging in t equals 0, the sign vanishes, right? So the second term will just die. And the cosine is 1, so I just get C1 times e to the 0, that's 1. So C1 equals 0. Okay, so this can only hold at times 0 if C1 is 0. So that means we have C2 e to the alpha t sine beta t equals 0. Now, if this is true for all t, then it should still be true after I take a derivative, right? So let's take a derivative. Now, I could do what I was doing before with these kinds of problems and just plug in like different value of t other than t equals 0, but I'm just showing you a different way of doing it. Here I think it's nice to take a derivative. So if you take a derivative, then you have to use the product rule. So you get C2 e to the C2 alpha e to the alpha t, that's when the derivative hits this term, times sine beta t. And when the derivative hits this term, this factor here, we get beta cosine beta t. And then plug in t equals 0 for that. We get, this term dies because it has a sine, and the cosine is 1, and then this is 1. We get C2 beta equals 0, right? And if beta is non-zero, then we get C2 equals 0. Is beta non-zero? Well, remember, we're imagining that we're in the case 3 here. If beta were 0, then we would be looking at real lambda, right? Which would be case 1 or 2. So when we say complex lambda, we mean lambda is not real. Yeah, I guess, technically real numbers are complex numbers. They just have they just have imaginary part being 0. So, I actually think this is a poorly named case. It should be not complex lambdas, but non-real lambdas. The idea is that beta is non-zero here. Okay, back to where we were. So here, beta is non-zero, therefore, since we're assuming beta is non-zero, C2 is 0. And that is our argument for the linear independence of these two functions. So the answer is yes. And now we are even happier than we were here when we found that we had two real solutions. They are two real linearly independent solutions. So now we can write down the general solution. Let's actually go back to that first page here. Initially, we said in case 3 we have this complex general solution, but let's kill that. We want a real general solution, right? We want a real general solution. So we have now found it. It is C1 times some function plus C2 times another function. And I'm going to pull these functions right out of here, where we said if e to the alpha plus beta I t is a solution, a complex solution, then it's real and imaginary parts. These two are real solutions. So this one and this one are two linearly independent real solutions. E to the alpha t cosine beta t, e to the alpha t sine beta t. And there we go. There's a nice real general solution. So now probably some of you are wondering, what about the other complex solution? right? Like here we have two lambdas, alpha plus beta I and alpha minus beta I. So what about alpha minus beta I? I seem to only have used alpha plus beta I, right? So going back here, I used alpha plus beta I, and then I took the real and imaginary parts, and those are my two real solutions. But what about alpha minus beta I? Well, if I had put in a minus here, let's look at what changes. If I use a reasonably sized eraser, and I put in alpha minus beta I, then here I would have a minus, right? And here I would have a minus. And here I would have a negative beta t, right? And here I would have a minus, and here I would have a minus, and here I would have a minus, and here I would have a minus. Okay, so cosine, the cosine of negative something is just the cosine of the thing. Cosine is symmetric. If you take the graph of cosine and flip it horizontally, it's symmetric about the angle 0, right? So I can just remove this minus sign. But what about sine of negative beta t? Sine is not symmetric, it's called antisymmetric. The minus sign pulls out. So this is what I would have gotten if I tried to use alpha minus beta t. It's almost the same thing. I would have gotten the same thing here. So there's no new solution. There's nothing new to add in here. It's giving me no new information. But this one might be new. I mean, it's different. It's the negative of what we had previously, right? Well, all that would do is make me go here in my general solution, and I would have said minus here, right? But that adds no value, right? That provides nothing additional here, because C1 and C2 are arbitrary constants here, right? They can range over all real number values, positive and negative. So to write it with a minus sign here is just going to flip how I interpret C2, but it does not make my general solution any more powerful or less powerful. It does nothing. So this is why when we find ourselves in case 3, we only need one of the two complex roots of the characteristic polynomial. We only need to take one of them, and then take real and imaginary part of the solution you get.